So start recording. So I've already kind of said this, but I've started grading the test. I'm about like halfway through the test. And so the thing with the test is most of you did them on like a PDF or something. So I've downloaded the PDFs and then I've written on like the PDFs themselves. And so I've made markings on the PDFs. And so there's a place to reply in there. And so somewhere in there, you should see a reply to your test. And that should have like a copy of your test with all the markings that I've made on it and basically tell you everywhere where you got points off or something. And so hopefully that'll explain most of like what you're missing on the test. If there's any questions over anything I've marked, I've always got office hours. You can come stop by. I can talk about it. I'll have a copy. I can pull it up and see what the heck I did.
Is this Zoom open for office hours?
Yeah, so if you want to come by my office hours, just like come by the Zoom. I should have the Zoom open.
Okay.
And so last time we were talking about 5.3, we're starting to talk about exponential functions. And so I know I gave you all like a few examples, but like, you know, I guess the main thing that comes to mind right now is, you know, the COVID thing is growing at a sort of exponential rate, right? That's what they're talking about when they talk about how that's growing. And so hopefully maybe it gives you some understanding into what's happening in the world around you when we talk about these things. And so they're talking about it going up, and they're talking about, you know, the terminology of like flattening the curve. I'm hoping like this is bringing some context to like what's being discussed, hopefully. There was a famous bacteria example. I gave you one example of bacteria, but bacteria is something that grows at an exponential rate. The other thing, really common thing that they start out talking about is basically populations tend to grow at exponential rates. Like these two people create two people, and then those two people create two people, and then those two people create two people. And then each time your population is doubling, you get this sort of doubling thing that happens. Usually they start off with like a rabbit example because rabbits are really known for breeding, I guess. They're known for populating. So last time we did 5.3 exponential, and I said you're going to want to study that stuff for the stuff that's coming up, because the stuff that's coming up, let me switch. Oh, that's horrible. Well, it's autofocus. There we go. Maybe it's a little better. So this, what's coming up is logarithmic. And to understand logarithmic, we're going to make a lot of comparisons to the exponential functions. And so if we look at this, 10 to the minus 1 is going to be like 1/10 or 0.1. 10 to the 0 will be 1, 10 to the first will be 10, 10 squared will be 100. So if we're looking at this, each of these is getting multiplied by a factor of 10 each time we go up by 1. And so you might notice this as this is just a 10 to the x function. And so if we want to take these numbers and flip them, this is going to give us the inverse function of the previous thing we had. And so now it's kind of like we're reversing the question. It's like, well, what exponent of 10 would you need to get 1/10? Maybe I should write this as 1/10. Or what exponent of 10 would you need to get a 1? So 10 to the 0 would be 1. 10 to the first would be 10. 10 squared would be 100. So we can still see that, hopefully see that same sort of pattern happening here. But now we're asking, well, what exponent would you need? We're not given the exponent. We need to figure out the exponent. So it's a little bit of a thinking backwards of how to do these things. Okay. And so they say the common log of a positive number x denoted log x is defined by this. So if they don't give us a number on the log, and I kind of talked about it here, we do things in base 10. We really love that. I can't put both my hands on here. Okay, but you have 10 digits. We really love those like base 10 numbers, right? And it literally just comes from the fact that, like, humans have 10 fingers. You can literally do this in like other bases. It's really kind of an arbitrary thing. But here they're giving a definition of a log. And so this is kind of like I was saying. So maybe write it out a little larger. If I have log of 10 of x is equal to 10. This is my base. This is my exponent. And this is the thing that I want to know, right? So another way to write this is my base, this is my exponent, and this is the number that it should equal. And we're doing this with base 10. If you want to think ahead just a few seconds, you can think about maybe doing this with other numbers. It is possible to have different base logs. Okay. But if we have base 10 or we don't see a base there, we assume it's 10. That is the common log. Okay, and this is just something that kind of follows from, we know those things are inverses of each other. And so if we look at 10 to the x, if I want to inverse a 10 to the x, and I can put parentheses around this maybe if I wanted to, I'm going to take a log of it. And if I take a function and I take its inverse, these are doing nothing then, right? I'm doing something and then I'm undoing it. I'm just going to be left with that first thing that I started with, which was the x up there. Same thing here. If I have a log of x, this is kind of a weird thing to say, but this is called exponentiating. And so I'm going to exponentiate my log of x with a base 10. So I'm putting that log of x up in an exponent and letting that 10 be my base. And if I do that, those things work against each other. And so these are inverses. And so what I'm left with is just the thing that I started out with, or that x. So I'm doing something and then I'm undoing it. And so I'm going to be left with just the original thing, the x. And so that's the inverse property. We'll use that in a second. I don't think we're going to use that right away. And so there's a few ways we can do this, but this is log base 10. And so if we want to know what this is equal to, I would probably stick to that definition that they give you. But we're thinking, this is my base, this is my exponent, and this is what it's equal to. So sometimes people draw the little arrows like this, and they will say 10 to the what power is 10,000. Well, if you're in base 10, there's this thing called counting the zeros, right? If we count the zeros, there are 4 zeros. And so log of 10,000 should be 4. Or another way to say it is 10 to the 4th is going to be 10,000. Okay. I like this. So here's my meeting. So log of 7 to the 0. So this might look kind of weird. But I think if you evaluate 7 to the 0 first, well, anything to the 0, other than 0 to the 0, we're not talking about that. But anything that's not 0 to the 0, that's just a big fancy way to write 1. And so if I'm thinking about this, if I think about log base 10 of 1, this is like asking 10 to the what power is going to be 1.
Zero?
Yeah, so 10 to the 0 will be 1. So if I want to know what this is going to be 0. So log of 7 to the 0 is equal to 0. And I believe we talked about this, but maybe like a quick review would not be bad. 7 to the first, that's just a really stupid way to write 7. We can talk about 49. So each time we go up this way, we're multiplying by 7. If we're going into negatives, we're dividing by 7. So this looks like 1 over 7 to the first. If we do like 7 to the minus 2, that's like 1 over 7 squared, or 1/49. What the negative thing does is it flips it over 1. So I'm pretty sure we've gone over that before. But doing a quick review is probably not a bad idea. Because if we come to this one, we have log base 10 of 1/10. And so this is like saying 10 to the what power is going to be 1/10.
That's 10 to the negative 1. Then?
And so this should be minus 1. So log of 1/10 is a minus 1. Oh man. We threw out the thing with fractional powers. I will do this right quick, but technically we're not supposed to do this, so don't tell anybody. Saying 10 to the what power is going to be 100 cube root of 100, right? And so cube roots, you can think of these as fractional powers. And so what I'm thinking is 100 is 10 to the second, and then I'd cube root it. And I'm thinking this is going to be 10 to the 2/3. And so we kicked this out because we kicked out fractional powers in that whole section that had higher roots. But you can have things that look like fractions in here. And I think that's why we threw this in here. Woo! Daisy's coming. So I wouldn't worry too much about the fractions in here, but just like be aware that when you take logs of things, you can have fractions. You can have negative numbers. You can have whole numbers. Now let's think about this. Log of 0. And so this is log base 10. If I don't see a base, I can always write 10 there. And we want to know what this is equal to. So this is like saying 10 to the what power is equal to 0.
One.
Ooh, 10 to the 1 is going to be just another way to write 10. And so this might be a little bit of a jerk question. Because what can you tell me about this? If we have 10 to the first, that's 10. If we have 10 squared, that's definitely more. If I have 10 to the minus, that's like 1/10. Am I ever going to raise 10 to a power to where it's going to equal 0?
No, unless there's another magical imaginary thing.
Yeah, not that I'm aware of. We don't have that in our bank. This doesn't happen. When we raise 10 to powers, it becomes a number. It doesn't ever become nothing, right? And so there's a sort of problem. And even like the other thing, right? If we look at this thing graphically, hopefully that might make more sense. These are what exponential functions look like graphically. And so if we're thinking about this, is this ever going to equal 0? No, it's never.
No,
Yeah, it's never hitting the 0, right?
you
And
can't
so
shift those graphs down ever. The story on that.
if you do, it would be on like on the outside here. It wouldn't be like on this thing itself. It would be like a shift
Okay.
down. You could do a shift down, but it's going to change it so that it would be solvable. I don't know how to say it. You get like a -4 here or something, so you would add 4 over here or something, right? And you wouldn't have that equals 0 problem anymore.
Okay.
So you could do a shift, but it would fix the 0 over here, basically. So in general, if you have a log, and maybe now might be the thing to think about, the domain and range, right? And so if I think about the domain of my exponential, I talk about the domain being from -infinity to infinity. The range is, it doesn't ever hit 0. It gets like infinitesimally close to the 0, but it doesn't ever hit it. And it just shoots off to infinity. And so this is my exponential. And so if I want logarithms, if we know their inverses, we can use that fact to our advantage, right? And so my domain for my logarithms, and I might be putting the cart before the horse because I'm pretty sure we talk about it in a second. But my domain for my logarithms is only 0, doesn't include 0, anything above 0. And so if I'm plugging in 0, this is that thing you can tell me it's undefined, right? We don't have this defined within the definition of our logarithm. Oh, I didn't even think about, I could have done maybe like 10 to the 0. That's another common thing people say. Anything to the 0 would be 1, right?
So is anything log 0 undefined, or like you said, if it was log 0 plus 4, then it is defined? Like you can figure it out, or is it just log 0? Everything is undefined.
So they would have to add the 4 inside of the log, right?
Okay.
So
Okay.
it wouldn't,
Thank you.
yeah, but log of 0 of anything pretty much is going to be undefined because you're never going to get something to a power that is equal to 0. Like the smallest power we can get is 0, and 10 to the 0 is going to be 1, right? It's never going to go below that. You can get fractional amounts, but you can never hit the 0.
Okay. Thank you.
Yeah. Okay. So now they want to go into different base logarithms. So this is the same thing. If I have anything down here other than 10, so now they're calling it A instead of 10. But this should look exactly the same. Now we're just replacing 10 with A. And so it's the same property. You can still do the same circle sort of thing. This to that equals that. So A to the K equals X is what that tells me. Or X equals A to the K. A is greater than 1. Okay. And K is a real number. Okay. And so this is a common log with a base of A. And so probably not a lot you can do with that. You're just looking at symbols. But here we have the same inverse property. Whew. And there should really be a log base A on this. An A there. Log base A of a to the x is going to be x. So we have this thing called a to the x. We want to undo that base of a, we take a log of it. Or we have a log of a log base a of x. We exponentiate it with a base a, and it should undo it. They're inverse functions. They're working against each other to give you just the original thing that you started with. Question mark here. Do your circle thing. I think is probably the way to go about these. 3 to the what power is going to be equal to 81?
Three to the third. You say
The
third?
third is 27, I believe, right?
Oh yeah, not a third. I meant 3 to the 3 power.
Oh no, that's
Oh,
27.
it's 27.
Yeah.
Oh yeah, you're right. Fuck.
Three.
Oh, I know.
Here's a trick. 3 squared is 9. 9 squared is 81. You just squared a square. That's a power of 4. I don't know if you want to do that, but you can think of force or powers of a force as squares of squares. It's kind of a weird way. But this should be to the 4th power. Three times 3 times 3 times 3. You can group 2 of the 3's together, group 2 of the 3's together, right? You can think of it as like a square of a square sometimes.
Cool. So how do we write the answer then? That's the answer. 3 to the 4th is equal.
Okay, so we want to find log base 3 of 81. That is equal to the number 4. We're looking for that exponent, is the thing we're looking for.
Okay, thanks.
So this is like asking, what was my exponent on a base 3 to make it an 81? Same thing here. We want to know 4 to the what power is going to be 1 over 64. Do I have? And so 64, if I want to know how to rewrite 1 over 64, that is 4 to the 3rd to get to 64.
Four to the negative 3.
Yep, and so it's going to be 4 to the minus 3 if I want to convert this to something on top, right? If I want to flip it. And so the number that we're looking for here is the exponent. So the exponent that we figured out was minus 3. I feel like I gave you these two in reverse order. Log 4 of 16 is like asking 4 to the what power is 16. The solution for this one should be what?
Squared, 2.
Yeah, 2. And now, just to be weirdo, I think they threw this one at you. And so this one, you could try to do something weird, but I think they want you to realize that if we have a base E, they don't write log base E, right? They're going to write ln, right? And that stands for natural log, or it's a log base E is essentially what this thing is. And so if we're doing the log of base E, and then we have a base E, and this is to some kind of number, what do we know about like these two things right here? The ln and the E, they are inverses of each other. And so if they're inverses, if we plug 0.67 into an e as an exponent into an e, and then we take the natural log of it, this is that inverse property that they're trying to get at. And so this is the thing. It should just be that number.
So ln e to anything is always, the answer is the anything it is to.
Yes, and that's coming from like this property right here. So we have log base e of e to the x. It's going to be that x. And so it's coming from this property. They're just using natural logs, which is a different base, right? But even if I have, maybe give you another example. Log base 2 of 2 to the, I don't know, pi. Just to throw in a weird number. This is going to be that thing that's up there. It's going to be the pi. It's whatever the heck is up here. These two things are inversing each other.
So Euler's number is the 0.67.
The Euler's number?
Yeah.
So Euler's number is the E, right? It's like the
Yeah.
2.718.
Oh, but natural log is Euler's though, so it's Euler's to Euler's. That what how?
Yeah, so this is the natural log with the E or the natural exponent, right?
Okay, I think.
So if we do ln of 2 point, let's do it. 7182812828. It's probably going to give me something close to 1, right? It should give me 1 because these are inverse. If I throw 1 into my E function, it's going to give me that crazy 2.718. This isn't the whole number because it's an irrational number. So we're just rounding it, but it's close to 1, right?
Yeah, yeah.
They're inversing each other, right?
How many known irrational numbers are there outside of pi and Euler?
Infinitesimally many.
Oh, all right.
I'm pretty sure.
Okay.
Because you can prove, there's proofs that you prove that they're dense in each other. And so if there's an infinite amount of rational numbers and there's an irrational number in between each one of those, then you have infinitely many, right?
Yeah, sure, that makes sense. I just thought maybe they were special.
I mean, they are special, just, I don't know. But there's not like a finite amount. There's definitely infinitely many. Okay, so we want to think about this. And so I've said a little bit about the domain. And so the thing that we have to plug into our log, where's that page? And so if it's just an x, my domain is 0 and above. So if it's an x in the log, I'm going 0, not including the 0, and above. So anything positive, right, I can throw into my log. And so we want to be able to say that. So the thing that I'm plugging into my log, it's not an x anymore. It's an x plus 1. But I said this has to be greater than what number?
0.
Got to be greater than 0 to keep it positive. If that's true, we can subtract 1 from each side, but this is going to give us what? X has to be greater than a minus 1. And so there's a few ways we can write the domain. If you wanted to just say x is greater than a minus 1, that's fine. if you want to say what, -1 to infinity, give it an interval notation, that's also good.
Maybe I'm confused because if it has to be greater than 0, then how can -1?
So the thing inside of here has to be greater than 0. If it's an x, then x has to be greater than 0. If it's an x plus 1, then the x plus 1 has to be 0. And this comes from, we can't plug in -1, but if you do try to plug in a -1, that's going to give you the 0. Anything larger than a -1, like a -0.5, we could try. That's going to give it positive. Yeah, 1 minus 0.5 is going to keep it positive, right? Anything
on.
over this is going to keep it positive. And so it goes back to -1 because we're doing those shifts on the graph, right? And so previously, and this probably ain't a bad thing to do, but like logarithms, they look, I believe they look sort of like that. And so what we've done is we took that original logarithm graph. And so originally we couldn't go to the 0. It like plateaus out here, right? It's got a asymptote. But now that we've shifted it back one, our domain changes, right?
Okay, thank you.
You can think of these as kind of like graph shifts, maybe, is one way to think about it.
Right on.
Yeah. But the argument and the inside of the log is the thing that has to be greater than 0. Yeah. And so if that's the way it's going, this argument has to be greater than 0. That's a little tricky. So if we think about it, this is squaring things. If I have a negative number in square, it's going to become positive. If I have a positive number in square, we're safe. There's really only one sort of thing here that's happening, and it's a bit tricky. But when x is positive, it's okay. When it's negative, it's okay. X cannot be 0. Yeah, this one's a little bit tricky. So we're not doing the 0. But I think maybe it brings up a valid point. It's a little tricky, but it brings up a valid point. Like typically we think about things as positives, zeros, and negatives, right? You got to think about those three things like separately quite often and try them out. I'm not sure that would be like the ideal test question, but it might be a homework question, right? Okay. Oh, use the inverse property. I feel like I led you up right up to this thing. If we have 7 to the pi and we take a log base 7, hopefully you see the inverse property is this thing is inversing this thing. And so if I cross all that out, the only thing I'm really left with is pi. Similarly here, so they're trying to lead you up, trying to do it with some simple inverse properties to kind of lead you into solving these things eventually. And so we're going to have equations with these, and we're going to want to solve them. So if this is a log base 9, and we're exponentiating that with a base of 9, this log base 9 and this base 9 are working against each other. And so if I look at how those are inversing each other, I'm going to be left with the 4x. And the last thing here, you can have bases that aren't whole numbers. This isn't the prettiest thing, but if you have a calculator, sometimes it's easier to do this. If you're doing this by hand, people would probably be mad at me. But we have calculators. We can absolutely do these, and sometimes it's easier to do it this way. I've had fellow professors look at me weird when I do this, but everyone has their own way of doing it, I guess. So this is log base of 1/4 and a base of 1/4. And so hopefully you notice this is a base, log base 1/4, a base of 1/4. Those two things are working against each other. This is going to leave me with that thing that's up there, which is 4.6. Okay. And so we have our basic log graphs. Our basic log graphs look like this. They're the inverse of the exponential. And so maybe to think about what your exponential looks like. So remember, this was our exponential. So we're flipping this x and y. And so now this thing, this asymptote here is going to become an asymptote here. Instead of picking up really quick, it's going to pick up really slow. And so in this one, a small change in the x was a large change in the y. So here, a large change in the x is going to be a very small change in your y. It's a very, very slow growth. And so we want to know like the basic shape of the log function, which is this. But we don't want to know like we don't want to memorize like how every little thing on the log does. So we're going to do some transformations to get graphs that are not just the not just the regular log function. And so if we're doing this, this is a -2 log of x. And so the first thing you ask yourself, is this inside the log or outside of the log? Well, I can do this. And so hopefully if I can put parentheses around the log and not include that thing in there, hopefully you start to see this is going to be on the outside. If it's on the outside of my function, it's going to be happening to my y values. And so hopefully we can see this is a -2. So the minus is a flip, the 2 is a stretch. So 10 to the first is going to give me 1. 10 squared or 100 is going to give me 2. And so this is the original log base 10 of x graph. If I want to flip it, 10 is going to give me a -1, and then 100 would give me a what? A -2? I want to flip it, and then I want to stretch it. And so instead of a -1, I'm coming here at -2. Instead of -2, I'm coming down at 1, 2, 3, 4. And so it should be stretched. Not the straightest graph, but it should look something like that. So we're going to flip it, and then we're going to stretch it a little bit. Solve each of the following if possible, right? Okay, so 10 to the x equals 10,000. I feel like we've had this problem before. So this one you could probably do. You could probably just figure this out, that my x has to be what value? I think this is one that we did already, right? X to the what number is going, or 10 to the what number is going to be 10,000? Start calling on people.
The fourth.
Yeah, to the fourth, right? 10 to the fourth, you can count the zeros. So this one is like not too hard to do by hand. But if we think about something like this, 10 to the what power is going to be 125. That's a little bit harder to do because we know 10 to the first is 10, 10 squared is 100, 10 third is 1,000. And so you might have figured like it's between 2 and 3 because it's got to be between 100 and 1,000. 125 is between these two numbers, so my x has to be between 2 and 3 somewhere, probably closer to the 2. Huh. This one is not so easy to figure out. And so we want some sort of method to get through these. And if I have a 10 to the x, start with this one. If I have a 10 to the x and I want to get rid of that 10 to the x, guess what I have to do to get rid of it? I have to take the inverse. So this is log base 10 of this thing. And I also have to take a log base 10 of this thing. And if I take a log base 10 of this thing, this is my identity on this side. This is something I've already done previously, and we figured out that thing was 4. And we figured out that thing was 4 by rewriting it this way, right? So likewise, we want to do something here. So in order to do this, I have to take a log of that 10 to the x, and I also have to take a log of 125. And so you might have figured this is not going to give you an even number. And so you probably want to start using your calculator at this point, because I don't know a whole lot of other ways you're going to find that. So log of 125 is going to give me this number. And so this left side, this is my identity over here. If I wanted to write a log base 10, that's fine. That's giving me an x. This is giving me this crazy number over here, 2.0969, somewhere around there.
Is there a preferred number of decimal points we go to for these sorts of answers?
Not really. I would have to specify what I want on that. I think that's probably pretty much like whatever your application is. You know, you kind of have to use your judgment call a lot of times on those sorts of things.
Okay.
But yeah, unless I say there's not really a standard. Okay. So 10 to the x is 1 minus pi. We want to do the same thing. We have this exponential thing by itself. We take a log base 10 of both sides. A log base 10 of 10 to the x is equal log of 1 minus pi. Oh, this is interesting. Log of, if I try to do this in my calculator, I guess that's the one way I could show you. I'm going to do 1 minus pi in my calculator. Where's the pi? You could probably think about what this is going to give me before I even do it. Non-real answer. Why is it giving me that? I have 1 minus 3.14. This is going to be log of, I don't know exactly what it is. Like a negative 2 point something. 1 minus pi. And so I'm getting a log of a negative. And if I get a log of a negative, right away you should be able to tell me this is undefined. Okay. And so maybe you've noticed, and so this is something you're going to have to figure out kind of on your own. I can give you some assistance maybe, but you might have noticed like your calculator only has a log and an ln. This is the log base 10. This is the natural log, right? And if I go second, it gives me the inverse functions. And so 10 to the x is the inverse of log, and e to the x is the inverse of the natural log. And so if you have log base 10, you can use this. If you have log base e, you can use that. If you have any other base log, you're gonna have to do something called a change of base, which we're gonna do in a minute. We'll do it before the day's done. But you can't just plug that into your calculator. Well, you can't plug that into my calculator. There's certain calculators that allow you and have the function to do different change of bases. They'll actually have the bases in there. Okay. So enough said about that. Let's look at this. And so this says 4 times 10 to the 2x minus 3 plus 4 equals 16. So there's this big ugly stuff, but hopefully you notice the thing that like differentiates this from the previous problems is that in the previous problems we had just that exponential thing by itself. In this problem we have other things kind of tacked to it. And so we want to get this thing just by itself first. That's our first goal. And so this is 4 times something. And so if it's really bothering you, I don't know, you can come up with another variable. 4u plus 4 equals 16 or something. And if we do that, hopefully you can see the next thing is I want to do what? Subtract this 4, and then I want to divide by that 4. And so let me jump back into this. If you want to use a different thing, you can. I think I'm just going to continue with this, though. So I want to subtract 4. And then I want to divide by 4. Divide by 4, it's 3. Okay. Now I'm at where I was in the previous problems. So I have a 10 or a base 10 by itself. I want to take log of that thing. Log of 10 to the 2x minus 3 is going to be the same as log of 3. So take log of both sides. If I take the log of both sides, and this is a log base 10, just to hammer that home, that's a log base 10, and this is a base of 10. And so those two things are working against each other. The thing that I have left on this side is that 2x minus 3, and this is equal to, ooh, almost messed it up, log of 3. Whatever the heck that is. That is not an easy, pretty number. We'll do a little more solving. And so if I want an exact solution, I want to solve for my x. I want to add 3. Log 3 plus 3. This is 2x. And then the last thing I want to do is divide by 2. So x is going to be, I guess you could write them separately if you wanted to, but I'm just going to do them all as one sort of thing. And so if I want an exact solution, that's going to give me an exact solution. And if I want an approximation, then I'm going to have to run to my calculator because I'm doing logs of 3. It's not going to be an even number. That gives me about 1.739, right? I want the exact solution when I see it. If you give me the approximation, that's okay. But this is the thing I really want to see, is the exact solution. It tells me you know how to do those algorithms. So maybe just like a quick recap of what we did here. We have this crazy thing. We need to get just this exponential term by itself. So we subtract the 4, we divide by this 4. Now we have the exponential by itself. It's a base 10. So to get rid of the base 10, we take a log base 10 of both sides. We take a log base 10 of both sides. It gets rid of our base 10 like we were wanting to here. Now we're left with that 2x minus 3. This side is just that log of that side, which is log 3. And then now it's just like a first order sort of linear equation with a crazy number over here. Now we're adding 3, we're dividing by 2, and this will give us our final solution. So that one, it's got a little bit of work there. Okay, we're getting close. Okay. So this is log of x is equal to 2. So the first thing you might notice is our log terms are all by themselves in these first 3 problems. So we did a few problems where we solved exponentials. We take a log. If we have a log, there's a few ways to do it. But this is a log base 10. If you want to do your circle thing, you can do your circle thing. Log base 10 of x equals 2. Means 10 squared is going to be equal to x. So if I want to know what x is, it's 10 squared. Another way to say that is x is 100. You can use that pattern, that circular pattern. The other thing you can do, which is a little crazy, which I do sometimes, log base 10 of x is equal to 2. We can raise everything, exponentiate it with the base 10. If we do that, you're going to see this identity thing happening here. This and this are inverse functions. They're working against each other. And I'm still getting, on this side, I'm getting x. And on this side, I'm getting 10 to the second power, which is the same thing, and this is the x equals 100. Same process, just a little bit different way of looking at it. Same thing here. If I don't see a base, it's a base 10. I can do my circular thing. And this is saying x is equal to 10 to the minus 1. 10 to the minus 1 is another way of saying 1 over 10 to the first, or 1/10. Now this is log base 10. If I want to look at this, this is 10 to the 0.2 is going to be x. And so for exponents that are fraction powers, you're probably going to want to pull out your calculator. But 10 to the 0.2 is going to be something like 1.585. Okay, so this is the thing same sort of pattern as that previous page. We did a bunch of exponentials, and then we did like a little more convoluted formula with an exponential in there. Now we have a little bit more convoluted, and it's got a few more things in there. But we're just looking at this, and like if this is confusing you, we're trying to get this by itself. Look at that just like it's a variable in its own. Like make this its own variable. So a half times u or something. Half of u plus 1 is 3. If we're solving that and it's a first order linear equation, the first thing we're going to do is subtract 1 from each side. So a half of log of 2 minus x is going to be equal to, I believe, 2. And then this is a half of u. If we're having something, the opposite of having something is to multiply by 2. And so if I multiply by 2, both sides, this is going to give me log of 2 minus x, and this is going to equal 4. And now comes the point. I wanted to get my log by itself. I've gotten the log by itself. It is a log base 10. Now we use that definition of logs. You can do the circle thing if you want. But 10 to the 4th is going to be equal to this thing in here, which is 2 minus x. 10 to the 4th, I think we talked about that number enough today. 10,000 is equal to 2 minus x. And so I'm just solving for x. I'm subtracting 2. That gives me what? 9998 is a minus x. And I believe to simplify or to solve for x, we multiply negative both sides, minus 9,998. Enough time to get through these probably. Okay. Okay, so now we're doing logs or exponentials of different bases other than 10. So now we're going to probably talk about that change of base formula pretty quick. But this one, I think, is straight 2 to the power. We can probably do this one in our head, I believe. 2 squared is 4, and then we square that, that's 16. I believe it takes 4 2s to get to 16. So that one, if you thought hard enough about it, you could probably do it before even today's class, right? But we want some sort of way to get at things. Okay, that is an equal sign. And so this is a base of 2. The thing that undoes bases of 2 is a log base 2. If I take a log base 2 of both of these sides, I'm going to take a log base 2 of 2x, and I'm going to take a log base 2 of 16. This, I'm hoping you see it. You have those inverses. These are working against each other. You have that identity property in here. And so this side is going to be my x. This is the side that, if we evaluate it, will be 4. And so in your calculator, you could do these by hand, but let's pretend you can't. In your calculator, if you wanted to do this, there's a change of base formula, and the change of base formula is called big log over little log. That's what I'm going to call it. Big log over little log. If we want to change the base, you can do log of 16 over log of 2. That should give you 4. The other way, and you can do that, you can do it any base you want, actually. You're changing the base, so it doesn't matter. You just have to keep the same, right? This should give you actually the same answer. And I know it trips people out, but If you're changing the base, then it doesn't matter. Just don't try to do anything weird and combine logs and ln's and or whatever. Keep those consistent, right? And then the same line. Keep it log and log and ln and ln.
And the big number always goes on top. That's why you said big over little.
Yep. Big log over little log is what I learned back in, I don't even remember now. This is completely wrong terminology, but it makes sense to most people. And you'll remember it a lot better if I say it that way, probably. E to the x. They're being a little tricky here. We want just the exponential thing by itself. We want just this by itself. So the first thing I want to do is divide by that 2. So e to the x equals 7/2. If I want to do an e to the x, the inverse of e to the x looks like ln. ln. And this side's e to the x, this side is ln of 7/2. This side is giving me my x, this side is giving me whatever the heck ln of 7/2 is. So if I want an exact solution, there's my exact solution. If I want an approximation, there's my approximation, 1.253. Typically, if I'm asking, and I've said this a little bit, but typically if I'm asking you to solve it, I want exact. But sometimes we might be doing word problems or something, so we might need this. It's good to know how to do both, I guess is what I'm trying to say. Same thing here. We have an exponential. We want to look at this as its own thing. We want to get it by itself. So this was a 5u minus 6. The first thing we would do to both sides is add 6. So 5 times 3 to the x equals what, 30? We still got this multiply by 5 we want to get rid of. So if we want to get rid of a multiply by 5, we divide both sides by 5. 30 divided by 5 is 6. Oh man. 3 to the what power is 6? If you tell me 2, you're going to break my heart a little bit. 3 squared is 9. Don't tell me that. So what do I do to get rid of this 3 to the x? What do I take of both sides? I have to take a
Log.
A log base?
Oh.
3, right? Okay. That's a log base 3 of that side. I also have to take a log base 3 of this side. And so this side is giving me my x right away. This side is giving me something crazy, but I can put it in my calculator and figure out an approximation if I wanted to. So this is log 6 base 3. Or I could do a log of 6 divided by a log of 3. That will give me an approximation. So this is about 1.631. And again, you're going to have to look at your calculator and see how your calculator does things, because I know some of them will actually do these little logs now. Some of them you're going to have to do this change of base formula to figure it out. Okay. Last few problems. I think the easiest thing to do with these is we already have the log solved for. Just do your pattern. 6 to the third is going to be my x. What is that? Third is 36 times another 6 is what, 216? That's it. X is Same do here. X is going to be 3 to the minus 4. This is my suggestion. Do these things one at a time. And so when we take care of that negative, I'm hoping like this is the thing. You see this negative, and I'm hoping this is like your first, like, I hope this becomes like second place. Put that 1 over. The second you see that negative, put that 1 over. Make your exponent positive. Take care of that negative. So I'm hoping like this becomes like second nature to you right here. As soon as I see that negative, I'm going to put 1 over and make it positive. Now I'm figuring out 3 to the 4th. 3 times 3 is 9. 9 times 9 is 81. I believe 3 to the 4th is going to give me 81. So this is ln. This is a base of e if you want to think about it. So if you want to do it, you can do it with base e. You can do this little circle thing. But x is what? E to the 6.2. So I have to figure out whatever the heck e to the 6.2 is. It's around 492.75. And this last one. So they try to make it a little bit harder. They tack on some more stuff to your log. So we want the log by itself. This log is being multiplied by a factor of 6. The first thing I want to do here is get rid of that 6. I have to, if it's multiplying, I have to divide it. 12 divided by 6 is going to give me 2. So I'm dividing both sides by 6. Now, I have nothing multiplying by my log. I have nothing adding to my log. I have this log by itself. If I have the log by itself, I can use my log property. This says 2 squared is going to give me 3x. So this is saying what? 4 is 3x. And if we want to solve for x, we have to divide by 3. So I believe x should be what? 4/3. So what I want to say about exponents and logs, I kind of said last time, like exponent and with exponentials, there's an example that I give to my other class, which is a pretty famous example. I might try to post it up for y'all if y'all want to do some recreational math for fun. But it's a pretty interesting example, and it gives you a lot of context into like how exponential functions behave. There's a bacteria in the bottle problem that I give my other class. It's about exponentials. But there's one thing I can say is that like I can almost guarantee most of the people will get it wrong when I ask those questions. And I can, not only will they get it wrong, like I can tell you what answer they will give me. Like, and I'm not saying that to be a jerk or anything. Like I'm not trying to sound like a jerk, but like it's something that is a really common misunderstanding, right? And part of it's because we understand linear and those linear sort of progressions really well, and we understand them kind of well on a sort of intuitive level. And when we talk about exponential and logarithmic, we don't really understand these things as intuitively well as we do linear stuff. You've worked with linear stuff all throughout your school career pretty much. And so there's been you've formed a sort of like understanding of it. This stuff, I can guarantee you, like people tend to like not do as well on this stuff. And part of it, I think, is because it's like the first time you're looking at this stuff for a lot of you. Like it's a new beast to you, and so you have to spend time with it. You know, you develop a sort of relationship with it a little bit. You're not going to understand this by just watching me do it and watching me do it on these videos. You're going to have to go home. You're going to have to do some homework on your own. You're going to have to work with this. Like you have to work with this exponential stuff. You have to work with this log stuff. I'm not trying to freak you out. I don't think it's undoable. I just think you have to spend time with this stuff. Like do not shortchange yourself on these topics is what I'm trying to tell you. Any questions?
Is the written homework from this section due Tuesday?
Yeah, and so these problems, yeah, they're on here. You had a few from 5.3 and 2 of them from 5.4.
5.3 is due today?
No, that's due next Tuesday. That's
Both
it.
of them by class time Tuesday?
Yep.
Okay.
Or yeah, I think I have it set to like the end of the day, to be honest.
Okay.
I think typically that's what I'm doing, is just setting it to the end of the day.
Okay.
Okay, I'm gonna hit the recording.